Hello and welcome to yet another lecture on basic electrical engineering paper code ESEE 101. Myself Prathita Roy, Assistant Professor of Dr. Sudhir Chandra Institute of Technology and Sports Complex, Department of Electrical Engineering. Today, my topic is sinusoidal modulation and three-phase voltage source inverter is an objective. After end of this topic, students will be able to understand the concept of sinusoidal modulation and three-phase voltage source inverter. So, we start with voltage control techniques for inverters. Inverter output, that is AC voltage, that can be controlled using various methods. These methods are classified as control of DC input voltage, control of AC output voltage, control of voltage within the inverter. So control of DC input voltage method. So the output voltage of the inverter is directly proportional to the DC input for any particular switching pattern. So the output AC voltage of the inverter can be varied by varying the input DC voltage. Control rectifiers can be used to provide variable DC voltage to the input of the inverter. Here the pictorial view, that is the block diagram to illustrate the use of phase control rectifier or chopper at the input of the inverter, that is the phase control rectifier. We are getting a controllable DC voltage with the help of voltage source inverter. We are getting controllable AC voltage. Same, the DC to DC converter, that is the chopper. From there we are getting a controllable DC voltage. Then it is with the help of voltage source inverter, we are getting a controllable AC voltage. So the control of AC output voltage of the inverter, an AC regulator may be used between the inverter and the load to have control of the voltage and load terminals. In this way, the AC voltage and the inverter output be able to control. So another question is the control of AC voltage within the inverter. So here the control of AC voltage within the inverter. So we have already discussed about some pulse width modulation, that is called the PWM. That is a popular method for controlling the voltage within the inverter. In this method, that is the PWM method, that is called the pulse width modulation method, that we have seen some We have already seen that the conception of pulse width modulation. So the pulse width modulation method, the output voltage, the pulse width of the output voltage is modulated, or output voltage is pulse width modulated wave. The magnitude of the voltage is controlled by varying the duration of the output voltage pulses. So there are three different methods of pulse width modulation technique. One is known as single pulse width modulation, followed by multiple pulse width modulation, and the third is the sinusoidal pulse width modulation, which is known as SPWM, sinusoidal pulse width modulation. So, in the first method, if I go to the wavefront, that is the basic PWM technique for the pulse width modulation. It is clear that if I concentrate on that particular figure to understand the conception of pulse width modulation, that when the switch 1 and switch 4 is turned on, first, and we've seen that, followed by switch 2 and switch 3, that is turned on. The first is the switch 1 and switch 4. Let us concentrate on the first graph where the switch 1 and switch 4 is turned on. But in case of the second portion, switch 2 and switch 3 is turned on. And we are getting an output voltage waveform pattern. So if I see the B portion, that is the second part of the graph, where the switch 3 that is turned on earlier, means the switch 4 is off and switch 3 is turned on earlier. Before the schedule, switch 3 is turned on. So, it means that when the switch 3 is turned on, the output voltage at the load that goes disappear. It is clearly seen. Before the scheduling time of the switch 3, the switch 3 is turned on means the output voltage at the load that we have obtained, that output voltage, it is goes disappear. Because the current from the source, the current will get a bypass to the switch is free. Similarly, for the next cycle, before the scheduled time off time of the switch 3, switch 4 is turned on. As a result, the output at the load means we will get no output at the load. Output voltage at the load gate disappear and the current will get bypasses through the switch 4. So in the figure 3, then figure B, the second figure, we have seen how the pulse when the switch that is on and off before the scheduled time, the switch is on, how the width of the pulse, that is the width of the output voltage that get changed before the scheduled time of the switch get on and off. Once the switch get on, how the width of the pulse is changed, we will see with the help of these two figures. So for any given frequency of the switching, the pulse width can be varied to control the AC voltage at the output of the inverter. It's clear that for any given frequency of switch, the width of the pulse, that is the pulse width of the output voltage, AC voltage of the inverter can be varied. Is clearly seen. So we will discuss about the sinusoidal pulse width modulation, that is called SPWM. So in case of the sinusoidal pulse width modulation, the output AC voltage of the inverter is controlled by varying the on-off periods so that the on-period pulses are longest at the peak of the wave. I will discuss it. That how we will get, this is the output of sinusoidal waveform, and how the waveform is getting, I will discuss. So just remember that portion that for the SPWM, the output AC voltage of the inverter that is controlled by varying the on-off periods so that the on-period pulses are longest at the peak of the wave. The switching instants are determined that I will discuss it. So we have a Vt is the reference modulating sinusoidal waveform having an amplitude of Vpm and a frequency of Fpm. So this is our reference sinusoidal waveform, which is shown here by the dotted line, that is Vt, having a peak value of Vpm, having an amplitude of Vpm with a frequency of Fpm. The frequency, that is Fpm, is equal to the desired output frequency of the inverter. Again, the conception is the frequency Fpm is equal to the desired output frequency of the inverter. And also there is another high frequency, that is Fc, of a triangular carrier wave of amplitude Vc. This is a triangular carrier wave. This is a triangular carrier wave having an amplitude Vc and a high frequency Fc. So we have two graphs. One is the triangular carrier wave having amplitude Vc and with a higher frequency Fc, and another is the sinusoidal waveform having an amplitude, peak amplitude Vpm and with a frequency of Fpm, which is the desired output frequency of the inverter. Now, how we are getting this output, the sinusoidal output here. So the general conception is that for the positive and the negative half cycle, we have to see for the both graphs the switching point that will be determined by the intersection of both two graphs, that is Vt and the Vct. So we have to find the intersection point for the switching points in order to determine the switching points. This is the one intersection point for the two graphs, that two graphs will intersect here. It is another, this one is the another, this one is the another part, this one is the another, followed by this one, this one in this way. This is for the positive half cycle, and this is for the negative half cycle, the intersecting point for the two graphs. So now we have to see for the positive and the negative half cycle where the value of VCT is less than VT. Value of VCT, that one is less than VT. Value of VCT is less than VT. So for that interval, value of VCT is less than VT. So for that interval, it is clear that the value of VCT is more compared to VT. This is the VT value and this is the value of VCT for that interval. So the output is 0. The output value is 0 for sinusoidal pulse width technique. Now here we are seeing for that interval from here to here, the value of VCT is less compared to the VT. So we will get a pulse width modulation, output voltage. We will get a voltage. We will get an output voltage. For that particular interval, the value of VCT is more compared to VT, so the output is 0. Or you can say the input is 0. The value is 0. The input pulse width is 0. The input voltage is 0. Now for that interval, from here to there, the value of VCT is less compared to VT. So we are obtaining a pulse of input voltage. We are obtaining a pulse of input voltage. So same pattern we follow for the negative half. This is up to the positive half cycle of sine wave. Same pattern we follow for the negative half cycle. So here, from here to here, this interval, the value of VCT is less compared to VT. So we are obtaining a input voltage, a pulse of input voltage in the negative direction, that is called the minus V in. For here to here, the value of the VCT is more compared to the sine wave, so the output is 0. From this intersection point to this intersection point, the value of VCT is less compared to VT. Then we are obtaining a pulse width. From this intersection point to this intersection point, the value of VCT is more compared to that VT, so the output is, or so we can say the pulse width, the input pulse width is 0. So in this way, that the entire pulse width, that is the entire input pulse width, or say the output same, that is obtained, the input pulse width is obtained. So this is the general conception of pulse sinusoidal pulse width modulation technique. So this is the general conception of sinusoidal pulse width modulation technique. But the VCT is less than VT, we are obtaining the width of that particular pulse. For that particular purpose, we are getting a pulse width that we have seen. We have to first determine the intersection point, that is the switching points, and we have to go from one switching point to another, from one switching point to another, from one to another in this way. And we have to see that from previous to next switching point where the value of VCT is less than VT. So that particular part will be there in the input, or we can say that this is the pulse width that we are obtaining where the VCT is less than VT for that switching intervals, and we will get the output of that particular portion. So this is the general sinusoidal pulse width modulation technique, or known as SPWM, sinusoidal pulse width modulation. So another portion of our discussion is the basic principle of three-phase voltage source inverter. So in case of the three-phase voltage source inverter, this is the general circuit of three-phase voltage source inverter. So in case of the three-phase voltage source inverter, six switches that we are used, the general purpose of three-phase voltage source inverter, the DC input voltage is converted to a variable three-phase AC voltage as a output. So our DC input voltage is converted to a variable three-phase output AC output voltage. A DC input voltage is converted to a three-phase variable AC output voltage. So there are, if we see the diagram, it is clear that there are three single-phase half-bridge voltage source inverters are there, and it is consists of six switches: switch 1, switch 2, switch 3, switch 4, switch 5, and switch 6, along with 6 diodes D1, D2, D3, D4, D5, and D6. Three loads are connected, and it is a neutral point. That is load 1, load 2, and load 3. And V1N, V2N, and V3N are the voltages across the load to neutral, that is called V1N, V2N, and V3N. So the switches are maybe of thyristor or transistor or MOSFET or IGBT. And we are seeing that six freewheeling diodes are there from D1 to D6. So the switching of are made, or the switch are made on and off at the intervals in proper sequence to produce the three-phase voltage at the output, which is displaced in time. The rate of switching, that is, determines the output frequency of the inverter. Many combination of the switching sequence for the operation of three switches are possible. So we are seeing a common combination of switching sequence for 120-degree conduction mode. For the we will see a common sequence for a three-phase voltage source inverter. There are different combination of switching for the six switches that will be available, but we will see a common combination of switching sequence for 120-degree conduction mode. So there is a 360-degree total time degree angular, that is called from 0 to 360 degree. So the each of the interval are of 60 degree. So that is means we have 6 intervals, each of for the 60 degree. So one is from 0 to 60 degree, another is from 60 degree to 120 degree. Third one is 120 degree to 180 degree. Fourth one is 180 degree to 240 degree. Fifth one is 240 degree, 180 degree to 240 degree, the fourth one. Fifth one is 240 degree to 300 degree, and the fifth one is 300 degree to 360 degree. So for the first interval, switch 1 and switch 6 is on and rest of the switch are off. For the second interval, switch 1 and switch 2 is on and rest of the switch are in off condition. For the third interval, switch 2 and switch 3 is on and rest of the switch are in off condition. So it is clear for the fourth interval, switch 3 and switch 4 will be on and the rest of the switches will be off condition. For the fifth interval, switch 4 and switch 5 will be on and rest of the switch will be in off condition. For sixth interval, the switch 5 and switch 6 will be on and rest of the switch will be in off condition, and again the sequence will be followed. Because the total rotation is 360 degree and we are taking an interval of 60 degree. So it is clear that when switch 1 and switch 6 is on for the first interval, that is switch 1 and switch 6 is on, switch 1 and switch 6, the output voltage is V1 in, that is from the 1N that we have seen, the voltage across the load that we have already seen, will be plus V in by 2. That is for that interval 60 degree. It is the interval of 60, 120, 60 degree interval, 180, 240, 300, 360, and again it is repeated. So for the 60 degree interval, just follow that particular line. For the 60 degree interval, the value of switch 1 is plus V in, means the voltage 1 in, that is called the voltage across the first load, that is V in by 2, that is clearly seen, that is V in by 2, this portion for the 60 degree plus V in by 2, and for the V2n, that is minus V in by 2, that portion for the V2n, that is minus V in by 2, that portion minus V in by 2 for V2n, and for V3n it is 0. For V3n it is 0. For V3n it is 0. So what is V12? V12 means V1n minus V2n. That is V in by 2 minus of minus V in by 2, that is V in. So for the 60 degree interval, the value is V in. For V12. So what is V23? That is V2 minus V3, V2n minus V3n, that is minus V in by 2. So that is clear here. For that interval, it is minus Vn by 2. Now what is V3? 1, that is V3n minus of plus Vn by 2. That is V31 is V3n minus V1n. That is 0 minus V in by 2. That is V in by minus V in by 2. It is clear. So V31 means V3n minus V1n. That is 0 minus V in by 2. That is minus V in by 2. That is minus V in by 2. So now for the second interval, it is clear that switch 1 and 2 is on. So means the voltage across the switch V1n, it is V in by 2, and voltage across the V3n, that is minus V in by 2, and voltage across the V2n is 0. So V1 in from 60 to 120 degree, that is V1n, that is plus Vn by 2. V2n is 0 and V3n is minus V in by 2. So for 60 to 120 degree interval, the switch 1 and 2 is on. That is means V1n is plus Vn by 2 plus Vn by 2. V2n is 0. V3n is minus Vn by 3. So what is the value of V12? That is this one minus this one. V1n minus V2n, that is Vn by 2 plus Vn by 2. What is V23? That is V2 minus V3. V2n minus V3n, that is 0 minus of minus Vn by 2, that is plus Vn by 2. That is clear. V23. And what is V31? That is V3n minus V1n, that is minus of Vn by 2 minus 0, that is minus of Vn by 2. That is clear. So, now for the third interval, when the switch 2 and switch 3 is on, the output voltage is V1n is 0, it is clear. V2n is plus Vn by 2, it is clear, plus Vn by 2. V3n is minus Vn by 2, it is clear. For the interval 120 to 120 degree to 180 degree. So what is V12? That is minus Vin by 2. Same process. So what is V23? That is V in, that is clear. And what is V31? That is minus Vn by 2. That one. So now for the fourth interval, that is 180 degree to 180 degree to 240 degree, from 180 degree, 180 degree to 240 degree. That is this one. When switch 4 and switch 3 and switch 4 is on, switch 3 and switch 4 is on. So the value of V1n is minus Vn by 2, is clear. Value of V2n is plus Vn by 2, and value of V3n is 0. So the same way the V12 is, you can write V12 is this V1n minus V2n, that is minus 2V by n, minus V by n, that is clear. V23 is Vn by 2, that is, and V31 is plus Vn by 2, that is this one. Now for the fifth interval, that is 240 degree to 300 degree, that is switch 5 and 6 is on, this one. Switch 5 and switch 4 and 5 is on, switch 4 and 5 is on for 240 degree to 300 degree. Switch 4 and 5 is on. The output voltage is V1 in is V minus V in by 2, that one. V2n is 0, that one. And V3n is plus Vn by 2, that is that one. So V1n is minus Vin by 2. So V12 is minus Vin by 2. For 240 degree to 30 degree, that one. And this portion, this one, V12, V23 is minus Vn by 2. For 240 to 300 degree, that portion. And V31 is V in, so this portion. So again for 300 to 60 degree, that is the sixth interval, switch 5 and 6 is on. Switch 5 and 6 is on. The output voltage, that V1n is 0, is clear. V1n is 0 for 300 to 360 degree. V2n value is minus Vn by 2, that is clear. V3n value is plus V3n by 2 plus Vn by 2, that one. And V of 2n is given, that minus Vn by 2, this one. And V of 3n, that is plus Vn by 2, that portion. So V of 1 2 is V in by 2, that one. V of 2 3 is minus V in, that portion, and V of 3 1 is V in by 2, this portion. So we have know that V of, just we have to follow how to calculate V12, that is the V12 is equal to V1n minus V2n. So V23, that is equal to V2n minus V3n, and V31, that is V3n minus V1n. So again, V12, that is V1n minus V2n, V23, that is V2n minus V3n, and V31, that is V3n minus V1n. In this way, we are calculating the total output voltage, that is the voltage waveform for 120-degree conduction mode for three-phase voltage source inverter. Thank you.